transfer path analysis is a technique where we are going to try and figure out where we have some perhaps unwanted noise that somebody hears. There's the ear over here, a floating ear without a body, or vibration that somebody feels. We have this unwanted noise, unwanted vibration. We want to figure out and diagnose how it's getting there. And transfer path technique is a technique that allows us to do that. And we would be looking at things like if we have motors mounted somewhere, is it coming through this mount? Is it coming through this gearbox mount? Is it airborne off of this propeller? Is it airborne off of this equipment getting to this guy's ear? So we have to break down all the components, if you will, inside a product in order to figure out where the problem is originating. So hopefully that makes sense. And you can use this, on anything from a boat to an airplane to a car to production equipment. And to do it, you just need to break down the problem actually into two key things. You have to identify the source that's generating this unwanted noise or vibration. And that source is outputting some sort of force into a structure that holds it, right? That force can be structural or it can be acoustic. So it can get either way into our structure. And then somehow it makes its way to the operator ear or some receiver location like a steering wheel or whatever in the case of a car or your seat. And the structure, well, we're going to quantify that structure with a certain type of measurement that relates forces over here to sound pressure or acceleration over here. Do you know what that special measurement would be, Charles?
I'd say FRF.
Yeah, FRF or frequency response function. That's a very typical thing we'll use to characterize this part of the problem. We'll measure operating data over here. So when we quantify what the source is doing, we're looking at operating data, and we'll talk about it, but it's actually the forces that are coming out of the source. So I was about to say you could measure vibration, but acceleration or accelerometers are a response due to the force. So we're going to do some things to try and really understand the force that's coming out of our structure. But yeah, in the end, we need forces and we need some FRS. We'll need a set of these that relate all these things together to be able to diagnose where our problem is. So I'm going to break that down a little bit further on the next slides. Again, this is called transfer path analysis. You'll also hear of things like time domain transfer path analysis or operational path analysis. They're all different forms of transfer path analysis. So let's get to some definitions. If I have a source, an electric motor, a pump, engine, whatever it happens to be, and I have a receiver location, and we'll throw in sound because, so let's say we're hearing this, the source can make its way over to this receiver location a few different ways. One way is airborne. And what we mean by airborne is when the sound leaves the source, it's starting in the air. So that's a path. That's the type of path. It's through the air, and it's where it leaves the source here. Okay. And the reason why I keep saying where it leaves the source or it's born is if you think of structure-borne, because that's another way. Here too, the source is interacting with the structure, creating vibration that eventually goes airborne. But we call this a structure-borne path because it starts at the structure. So it's where it's born in life, so to speak, is what we consider a structure-borne path. So starting with the structure, or we could have stuff that starts in the air but leaving the source. And I should have just said starting at the structure, but I meant starting at that source structure interface. Okay?
That makes
sense.
Yeah.
So far, Charles?
Yeah.
I haven't confused anybody with my inadvertent, well, maybe you should have a poll question at some point. Are you confused by Pete? So. Okay. So on these slides, I'm going to go through, kind of step through an example. I'm going to use some letters, and they all mean something different. And you'll see that there's something like F for force, A for acceleration, which is vibration, P for sound pressure. P over F would be a transfer function, or FRF, that relates force to an output at an operator ear location, for example. Operational forces is going to have this little sub O. So when you do a FRF, you use something like an impact hammer or a shaker, the force, and you're just trying to get the ratio here. But when you do an operational force, which is an important part of breaking down this path, that's the actual forces coming out of the source during operation. And then we'll talk about the total sound pressure from combining our paths together, and then the total sound pressure measured at the receiver or operator location. Okay, so these letters you'll see on the next slides here. So let's make a real simple example where we have a source again, pump, could be a engine, could be an electric motor. That source is attached to our structure. Here's the receiver location. And we need to know the forces that are coming out here. And we might be interested in knowing which attachment location is most responsible for what we're hearing over here. So we have the force during operation at attachment location number 1, and we have the force during operation at attachment location number 2. And we want to know which path is contributing the most. So I go out and I can measure those forces, or if I have a simulation model, I can create them. And notice this dashed blue line. It helps to think about, if you're going to break down a problem, do a transfer path, to think about making a mental cut that separates the source from the structure that holds it. So we made a dotted blue line there, and you can see where we cut it on one side of this line. We're interested in the forces, but this doesn't tell us the whole story. We also want the transfer functions at these attachment locations, because forces are coming in from the source during operation, right? They had that little O, but we want to know how much sound pressure gets generated over here. So we need a transfer function of P over F that relates to 2. That's non-operating data. That's really a characteristic of this structure, right? It might have certain resonances. So these are functions versus frequency, just like the forces. Some frequencies might be more sensitive to inputs than others. So we need that piece of information as well to these attachment locations. So if we had 3 mounts and it was crossing through here, we would have a third path, right? So again, we make that mental cut. So forces, operating, the FRFs, that's all the information we need. And we just go ahead and we'll take those transfer functions and forces, we multiply them together. So we take the transfer functions for each path, then we take the forces for each path. These are operational forces, and then we'll get the total over here. When we multiply them together, I could think of this as the contribution of path 1 to the total. And this here is the contribution of path 2. And I'm going to evaluate which one's the problem path by whichever one of these 2 quantities is larger. Is it P1 that's greater than P2, or is it P2 that's greater than P1? If they're equal, then I guess they're both equally responsible. So Charles, I got a question for you.
Sure.
If we know we want this P1 and P2, I guess during operation, why don't we just go out and measure that to begin with? Why do I have to do measure P1 or measure P2? Why do I have to measure an FRF and a force and an FRF and a force? Seems like a lot more work.
Yeah. I guess we need to know the contributions from each so that we can tell too, I guess looking at this equation, if it's a problem with the force coming through that location being high, or maybe it's sensitivity at that location. We can get that information.
So I guess that gives us a little more information, tells us if it's on the structure or the force side. But if I could measure this directly, at least I'd know where the problem path is. So It's kind of a trick question, Charles. The reason,
Yeah, you tricked
so
me.
this is, I know. The reason why we can't measure this operating data from path 1 by itself and path 2 by itself kind of has something to do with physics in the real world. I would have to, if I wanted to measure P1, I'd have to disconnect this mount, right?
Yeah.
And so let's say you had 4 engine mounts. Can you disconnect 3 of the 4 and then, fly your airplane? Or
Not very successfully.
yeah, it's pretty hard to measure this. That was kind of one of the things I was trying to hint at there. And same thing, if I wanted P2 here, I got to disconnect all the other ones. So I'd have to fly my airplane 4 times, each time with 3 different mounts disconnected, So maybe it wouldn't work out so good for me after the first data acquisition if I had disconnected everything. So not easy to get. What's that, Charles?
That you'd go through a lot of planes and pilots that way, yeah.
Yeah, but you'll get great data to figure out the noise issue. It'll be worth it. No. P1, P2, hard to measure. That's another reason we do this, but it does give us additional insight, like you said, into the actual forces and into the FRFs, whether it's the structure or whatever, right? So let's say we go out and we do these, we get our P1 and P2 here. If I was to look at this P over F1, let's say this was some huge number, just make up a number, 1,000 pascals of sound pressure at outputs for 1 Newton, like maybe at this peak. Does that mean that this P1, like this over here is maybe only 10 Pascal per Newton peak, right? Does that mean P1 will be the problem path?
No, not until we know what the forces are, yeah. We can't say that for sure.
Yeah, we can't say, because if the force is 0, well, this won't be very big, will it?
Yeah, not at all.
Yeah. So yeah, that's the kind of thing we're looking at, and you can't just look at the FRF. Can't just look at the force, because the opposite is true. This could be 1,000 newtons, but if the transfer function is 0, this path won't be very much. So we need to look at both things. Now, let me jump up here. Let's say we sum up our total from our model. Ideally, should kind of look like the total that we measure. And that's one of the benefits. If we have an actual system, we can actually go out and do the measurements and see what the total is. And then if we had summed it up and it looked like this, that means something, right?
Yeah.
That means we're missing a path. It could be another structural path we didn't consider. It could be airborne paths, like in this case. If there was only 2 mounts, then odds are it's something airborne. But one of the nice things about this technique is, if we did miss a significant path, we have the ability to go in and kind of check ourselves against reality, the measured total. We would expect the measured total and the total from the measurements that we make to be the same. Again, this is a technique that could work with simulation models, so it may not even be measurements that you do. You just need a set of FRFs and you need a set of forces. And you can even do what we would call hybrid models. And nowadays, hybrid means both gas and electric motors. Hybrid in this case would mean I could even use a combination of a simulation model with test data, right? Because I don't care where the FRF comes from, et cetera.
Right.
All right. So let's look at this a little bit more, how these paths work. So it's important to kind of emphasize this cut, because that's going to define what we can evaluate and understand when we go to do a transfer path. And so here you can see I have a cut around the motor. I have sound inside a cabin, and then there's even some mounts for this cabin right here. This transfer path is a 4-mount, 3-direction TPA. So I have 4 physical attachments, and then I have X, Y, and Z. So I showed just 2 before, but really there's at least 3 directions if you're doing measurements, 6 directions, 3 translational, 3 rotations if you're doing simulation. That's a 12-path TPA. Sounds good.
Yep.
Would I know anything about the forces coming into the cab in this case if I measured my operational forces over here and then I did transfer functions there to there? I would have no insight. Yeah.
Yeah, we got
Now,
another cut.
yeah. You'd have to do a second cut to have a second model, potentially, if you wanted to understand these. It may even make sense to make your cut like this from the get-go, because maybe from an engineering point of view, you can't mess with these motor mounts, but you can mess with the cab mounts, for example. And so if that's the case, you'd be better off making your cut this way. And consider the frame here that holds the motor as part of the source. You know, because maybe you can't do too much about it. Or you can do both analyses if you want. It's really up to you. But for a given transfer path analysis, you're going to have a set of FRFs, a set of forces. They can only really be through one layer at a time, if that makes any sense. You're either going to have your cut. You can't have your cut multiple ways, you know, or that defies physics. Or you could include both the cab and the motor mounts in the analysis at the same time. So you have to kind of think about that a little bit.
Yeah, I guess if you're getting paid by the hour versus the project, depends on if you want to do both.
And maybe sometimes it makes sense to do both. I don't know.
Yeah.
Let's talk a little bit about force identification. So one of the challenges with this technique is how do you get the force here? Well, you can, if you're lucky enough, you could fit a load cell in there, and you hope the load cell doesn't make this mount behave differently than the system normally would. So it has to be an unobtrusive load cell. In practice, a lot of times measuring the forces in newtons or whatever directly ends up being impractical. So we measure the forces indirectly. And indirectly means doing something like this, for example. We know, I think it's Hooke's law from quite some time ago, F equals Kx, displacement times spring rate gives us the force. So rather than put a load cell in, we can easily mount accelerometers on each side of a mount. You know, on one side, we'd call it the active side where the motor is or whatever, lots of vibration. And then if it's a good isolator, we'll have a passive side here where there's very little vibration, and we can measure the acceleration on both sides, double integrate to get the displacement, subtract them from each other to get this X to come. And then if we have the mount rate, so that involves yet a separate test, then we can get the forces that are coming through this mount. In common way, people will estimate the forces. You have to be careful when you go to determine the mount rate. So rubber bushing, you need to put it under similar conditions that you have during the operational conditions of the product, so that the stiffness rate that you use reflects what's going on during the actual operating conditions of interest. So you have like a mount, a piece of rubber like this, and you stick a motor on it that weighs a lot, it's going to squeeze it down, right? And the K here, when it's not squeezed versus when it's squeezed, this will be a different K. They won't be equal. You know, you want things like the correct preload, et cetera, that reflects the reality of the situation to get the right stiffness value. And they can test it in elastomeric test rigs like this one. You know, they put the mount in and will sweep through, but you have to make sure also things like the test fixture does not have resonances, for example, because you might get spikes in your data and things like that. When I'm using the test lab software, in SimCenter Test Lab, we have a module that's actually called Transfer Path Analysis. Now, this software doesn't actually acquire data, but it lets you take data that you've acquired, so FRF measurements and operational forces, and organize it and use that data then to identify the key paths in the structure. So that's what I'm showing here, a piece of software called Transfer Path Analysis. I look in my data navigator, you know, and I look in some of these folders. There is data in here. So there's FRF data that's been collected. So you have FRF data and you have operational data. When you let's see if I can do this here. So when you put this data in an input basket, and then you can start organize it. You could say, all right, I have this operator ear. I want that to be one of my targets. I have some paths here, and I can make these the paths that separate my source and my structure. You can see here I got a body 1x, 1y, 1z, 3x, 3y, 3z, 4yx, x, y, and z. There's 5 physical attachments, 3 directions each. So that gives me a 15 path TPA. And then indicators is really, the word indicator kind of sounds like indirect. If you do not have the forces directly, you can set up, I'm going to use acceleration, on each side of the mount in order to calculate the force. And over here, under this mount table, I can say, here's the body side, engine side, and what they correspond to, and identify those things. And then you bring in the data. So like in this case, I could see the FRFs. Does one of those FRFs stand out to you, Charles?
Yeah, that blue one. What is that? Body 1Z?
Do you think we found our problem path then?
We'll have to see, but it looks suspicious for sure.
Yeah, looks suspicious, but yeah, if the force is 0, won't matter. That's the FRF data up here, kind of quantifies the structure. Operational data, this quantifies the forces, and so you can also see the forces coming in. We go in and we put all this together, and I do have operational data that's accelerations and some mount rates and stuff, and go and do these calculations, and I get a beautiful chart that looks like this. Here is my measured total, Charles, and my calculated total. Do they look similar? From the amplitude standpoint, which is indicated by colors? Yeah, so we got RPM or Hertz down here on the x-axis. Coming out at us is the amplitude of sound or vibration. In this case, it's an acoustic target to a microphone, so it's showing us the measured and calculated total. And one of these pads does stand out. Which one is it, Charles?
That body 1Z again.
Yeah. So the first 2 rows, that's the measured versus the calculated total. The rest of the rows are all 15 paths, and it's showing me the one that's the biggest contributor here. If I have something like a double X cursor, there could be more than one spot. I'm interested in what's going on, so maybe up here or something. It'll sort the paths, like in this case, over this RPM range, which one's the biggest contributor? It's not body 1Z.
Yeah.
But as soon as I put the path over here, or the cursor's over here, body 1Z is the biggest contributor. Make sense so far?
Mm-hmm.
If I go to this path-specific area, I can also kind of break things down a little bit further and see what's happening. I can see the force that's coming in at this path and the FRF, and then these 2 get multiplied together. So this, I highlighted the path body 1x over here. The blue is the contribution of that path to the total. And red and green, I kind of can't remember which is which. One of those is the calculated total, one is the measured total. They look pretty close. Yeah. And then I can actually, well, in this case, I can say, well, I see that they're both pretty low. Maybe that's why they work. If I look at some of the other paths like body 1Z, how does its total for this path compare?
Looks like it is a major contributor in that RPM range there.
Yeah, and we can see actually relative to other paths, we want to know, you said to get some insight into whether it's the forces coming out of the source or it's the structure and its FRF, how sensitive it is.
Mm-hmm.
If I was to look at body 1X here versus body 1Z, what do you think it is, Charles? The structure or the source? This is the forces. This is the FRF.
Yeah, it's the perfect storm there because it looks like we have a high force and it's sensitive at that RPM as well.
Yeah, it definitely is the perfect storm.
Frequency.
Yeah. So in some organizations, you have the source guys like engine or motor people or fighting the structural people. You know, who's to blame for a given problem? In this case, you get to blame both. Isn't that awesome?
We don't want to, have any favorites. Everybody gets the same treatment.
TPA also lets you do some other things, like you can come here and you can say, all right, structural people, if you could reduce that sensitivity of your structure by 90%, and what would the new sound level be? And you can see if it would even be acceptable. So it does, maybe it's not realistic per se, but yeah, if you could reduce it 9%, would you even get to the dB level you think you need to be at that operator location in order to achieve the results that you want? So it lets you actually, once you've organized this data with the FRFs of the structure and the source data, you can do these kind of what if games and get some insight into what's going on. You have a path with mounts, you can identify mount resonances and things like that as well. So let me jump back over here again. I want to talk about another method other than mount method for determining forces. It's a method called the matrix inversion method. And what can happen, or one of the challenges with the mount method, is we could have a very stiff connection. We could have this source, motor, whatever it is, maybe mounted through metal brackets directly to the structure. Compared to a rubber mount, what's that going to do, Charles, if I mount it directly? Is it going to attenuate the vibration much?
No. It'll be very stiff.
Yeah, if you think of the active versus the passive side of the mount, the vibration could almost be the same. So maybe I measure it twice. Like one time I measure it, the active side is 10,000.2. I measure the passive side is 10,000.1. I do another measurement, it's 10,000. Is that much measurement noise if my measurement changed from 10,000.1 to 10,000?
No, that's a problem.
Yeah, it's very accurate, or it didn't change much. But when you do the subtraction here of 10,000.2 versus 10,000 and 10,000.2 minus 10,000.1, that little bit of noise actually changes the force estimate by a factor of 2. Do you think that that could be a concern, Charles, that our forces could swing?
Big concern.
Yeah. So with stiff connections, this idea of a mount method doesn't work because there's not much of a separation between the active and passive side as far as their levels go. There needs to be significant attenuation across the mount to get some kind of reliable forces out of the mount method. So a different method is something called, let's call it a matrix or FRF matrix method. Basically what we'll do is we're going to measure another FRF here that we, in addition to the FRFs that we measure for the path. So we're interested in the total at the operator ear here. And by the way, I want to emphasize this can be done for vibration. So if I had accelerometer or acceleration, I would have an A over F for these locations. Now I've introduced A over F again, but what we're doing is we're actually measuring it right at the same place that we're applying it. So right here, so that we can relate an operational acceleration at this mount location to the force. Can you measure A over F easily, Charles?
Yeah.
Yeah, that's just an impact hammer, right? Or shaker. And you just have the accelerometer right there and you can get your A over F. P over F, it's just a microphone over here and your impact hammer over there. In fact, you can even measure them at the same time. You apply the force with the impact hammer, and if you had both an accelerometer and a mic in place, you could pick up your A over F and P over F. And that A over F, we're going to take the operational accelerations at those same locations, and we can take those operational accelerations times the FRF to come up with our force. Do I have to do anything for this A over F in order to relate it to force using the operational acceleration, Charles?
Oh, I got to invert it.
Yeah, I got to invert it. So that's why we have this -1 here, and that -1 is going to make it flip the F over A. Was that an exciting flip there? And that will give us this operational force. And that's all fine and dandy. Not a free lunch though. Sometimes you could have an anti-resonance where this is like close to zero. What happens when you flip zero?
It's undefined.
Undefined, or isn't it like infinity?
Okay.
Undefined?
Yeah.
Pretty close to undefined. Anyway, the
You can't get
infinite force, is that, you encounter that a lot?
there. I try to avoid it.
Yeah, I try to avoid infinite forces too. Yeah, we know an infinite force isn't realistic, but because of the FRF information, that can happen sometimes. So that's where this word matrix comes in. Rather than relying on a single FRF per path, what we'll do is we'll take a whole matrix of FRFs and the operational accelerations. We'll flip the entire matrix to come up with the forces. And our hope is, I was to look at this FRF, for example. Let's say it goes to zero at a certain frequency like this. If I was to grab another FRF in this matrix and plot it on top of that, and this is where, I'm a true artist here, Charles, the dashed line. We hope that that's not going to zero, so that overall we can get a good estimate for the forces. And there's some rules of thumb, like if you're going to add some A over F's to condition this matrix to get good forces, it's probably good not to have them all located in the same spot, because all of these FRFs, if they're all four together, probably have the same anti-resonance. Instead, we want to scatter these additional A over F measurements all over the structure so that the chances of them all having anti-resonance at the same place isn't very high. And we don't want to include FRFs that might have a lot of noise in them, things like that. So that is the matrix method. Any questions about that so far, Charles?
No, none so far.
Good. I'm going to back up to the beginning of the presentation. Let's say, let's use a classic thing, powertrain noise. I think most of us, even though there's lots of electric vehicles out there, seemingly, a lot of us have gas engines still. If I had a gas engine, well, how many paths are there to get to the operator ear? Any thoughts, Charles?
It depends on your engine mounts. 4-mount, 3-mount system.
Yeah, you could have 3 or 4 mounts. So we have engine structure-borne potentially, right? 3 or 4 mounts.
Yeah.
Any other
Then
ways?
there's airborne, just off the block itself is airborne.
Yeah, so off that engine, got airborne. Any other ways?
For let me see, we got.
Well, we got underneath. I know we're thinking electric still, but we got this with gas. We have these big exhaust systems, right? That output, gases out the back. Ever heard of exhaust noise?
Yeah.
Yeah, that could be a way it gets in there. So we could have both intake and tailpipe noise that goes on. And then this exhaust, I think how does it stay? Is it part of the car, or how does it stay put? Or just trails? Mine trails along behind me.
Then you should invest in some good exhaust hangers.
Yeah, we got exhaust hangers, right, that hold the exhaust in place. But so sound or vibration could come through those exhaust hangers and then into the structure. So earlier we were showing this real simplified example where the motor, we just made a simple cut around it. But really, if you think about the motor with the transmission, and you can have a transmission mount, and then the exhaust and everything else, the cut is kind of sophisticated, if you will, for all these different paths. So that is a lot of potential paths. You got, tailpipe, transmission, mounts, everything else. So a real TPA model, I wanted to, at least what I was going to call a real TPA model, might look more like this. Is that a few more paths, Charles?
Yeah, that's certainly a few more paths there.
Yeah, and I could, I might have a lot of different spots where things are going on, and I can do stuff and see what's most responsible, etc. But yeah, potentially we're talking about a lot of paths. If it was just a few paths, we could probably figure things out without this technique. But when we have a lot of paths, we need something that can really rate them all for us. And it's possible, too, that we might even, part of what the software can do for you is you can create groups. We said, like, there's Airborne off of the engine. If I grab all the Airbornes around the engines here, just right there, I could call this engine Airborne. Create a group like that. And then I got like these engine structure-borne paths, for example. I can create a group. Got those exhaust hangers, which I need to run out and buy when I'm done here. Because you get other noises when your exhaust drags behind your car, Charles.
I would imagine.
It's more of a scraping noise. Tailpipe, intake. You get the idea here. And when we group things like this, we can then actually look at like the same thing, but now I might get some different insight. Like, oh, the engine structure-borne is most responsible. Engine Airborne second most. The ungrouped, I didn't bother to get them all in there, but intake, exhaust, etc. Does that kind of make sense to you, Charles?
That's very useful feature there when you have so many paths.
Yeah, and again, the idea was just to kind of give you an idea of what all could be involved or what a real model might look like. All right, now I'm going to go forward in the presentation. We were talking about structure-borne and airborne problems. I thought I'd spend a minute to talk about what's involved on an airborne path. In order to do an airborne path, you have to know a quantity called Q, which I'll introduce. But so now our nomenclature, you're going to see this Q. Q is an acoustic force. Explain that in a second. So that'll start appearing on the slides. And now we have, so these are, the Q is the airborne off of the source. The F is structure-borne off of the source. And then we have transfer functions, P over F, P over Q to relate to that. And then we got operational Qs, for example. But other than introducing Q, about everything else you've already heard of here. So what is this Q? If you think about structure-borne path, an input to a structure is a force, output is acceleration. And this is pretty important in TPA, by the way. You shouldn't confuse these two, because if you think about a structure, I just wanted to at least point this out, even though we're talking about the airborne stuff. If I apply a force here, there's a temptation to say, all right, I'll measure acceleration here, and I'm going to say that is that acceleration represents the force, because I don't want to bother to put the load cell in. And then let's say I'd instrumented something over here, A2. Well, when I apply a force here, I'll also see vibration at A2, right? The acceleration is not always a good indicator of the forces coming in, because, again, the system can respond. If I only applied the force here, I'll still see some response over here. So I don't really know the forces. So you have to be careful. Same thing, sound pressure is really a response of the system, but the true input is this acoustic force, called Q. Q means, let's say I have a speaker like this, and I want to know what it's outputting. Q is the area times an acceleration. So you take I break that speaker up into some groups here. I got an area for each thing, right? Dimensionally, which gives me a meter squared. And then if I measure with an accelerometer in the center of this area, I get meter per second squared. Multiply those together, get meter cubed per second squared. As a result of this cubing, which was based on an area, but now we picked up an extra meter, sometimes they will call this a volume acceleration, because there's a meter cubed term, which is a volume. And you do that potentially for 0.1 here, 0.2, the area. You can sum them up to get the total airborne, just like we did with the pads. before. So hopefully that makes sense. Here's an example of what a airborne TPA can look like, where in this case we're interested, they made the cut as the panels inside a cabin, and they wanted to know which panel was radiating the most noise. What do you think, Charles? Does that look like fun?
Oh man, yeah, looks like a really complicated game of Connect Four or something in the car.
Yeah, we got, all right, we connect 4, and instead of a checker or whatever you use in Connect 4, we put an accelerometer in the center of each one of these. And, you know, if I wanted to know the total here, I would sum up all these paths, the areas, the respective areas times their accelerations. And then I could figure out, okay, is it the floor pan or is it the dash that's creating the most noise? Okay. Looking at this slide, I think this has nothing to do with anything. It's just eye candy on top of the slide to confuse you. That's how you get the operational cue, but we also need, you know, to do a path, we have this cue operational, but we have to multiply it times something to get the total sound coming. And do you recall what that was?
We need that transfer function, frequency response function.
Yeah, which is P over Q. That's a little harder to get. And we make a tool conveniently at Siemens in part of this presentation called a Q source that outputs a known Q right here at this nozzle. They come in a few different models, but this is a pretty popular one to create a known Q. And if, again, to relate that, think of that as the acoustic equivalent of impact hammer. With an impact hammer, we got calibrated load cell here, right? We can measure the force. And with this, I can apply a known Q. Does that make sense, Charles?
Mm-hmm.
It's not a speaker. We're not measuring the pressure. But, well, it is a speaker in that it generates noise. But a traditional speaker, you might think, is generating sound pressure. But this is generating a calibrated Q, which is different than sound pressure. Sound pressure being the response, not the input. So with this Q, we can get the Q source, we can get the P over Q. And let's see how that might work on our simplified example. So I got my source. It's a great drawing, isn't it? I've divided the source into two areas, A1 and A2, right? And I'm going to measure an acceleration at each one of those areas, and I'm going to measure the area itself. So A10 is operational acceleration, A20. When I multiply the area times the acceleration, what am I going to get? I'm going to get Q, right? Then I'm going to put the Q source here, actually, and do a reciprocal measurement. This is kind of radical to get P over Q. The P over Q will be at, I actually put a microphone right where the accelerometer is, literally tape it in the same place, and I can get a P over Q. And then I take my P over Qs, right, that I measured, times my Qs, operational, right, from the accelerometers, multiply those together to get my P1 and P2. Now, you can have, I'm showing an example with just airborne, but you'd still do the same for structure-borne if you wanted in the simplified example, and you would have four different things. You'd have some P over Fs times Fs, plus P over Qs times Qs in order to get the total. If you look back here on these paths that we were looking at a second ago, I go to the model here. Notice in the same model, I got forces, and then I have the volume accelerations, the meter cube per second squared. So they're together, okay, in the same model, and I can see the airborne versus the structure-borne without a problem. Again, the Q is actually, in this case, the acceleration times area for each one of those. Okay. That makes sense so far, Charles?
Yep.
And
Was I muted when I was talking last time?
You might have been muted earlier, but I was enjoying the silence.
Sorry about that.
The lack of challenging questions. So it was refreshing, completely refreshing. So that's good. There's another way to use this, and this is kind of like with the matrix inversion method. Another approach I could take is, I know I can measure these P over Qs, and I put these with the R here because this will get confusing. This is a P over Q to this receiver location or the operator ear. And instead of measuring acceleration, because the accels may not last long on a hot engine, right? Instead of doing acceleration, Charles, I'm going to just put a microphone nearby, because those will really last long near a hot engine. So, and so I can measure a P there, but I need a Q coming out of that source. And so what can I measure, Charles, to relate P to Q?
A P to Q?
Yeah. I can measure a P over Q function, but I'm going to do it right at this location. So, initially I was getting the P over Qs to the target location, but I could also move that Q source, the nozzle, and place it right at that microphone location and get a local P over Q or a matrix of P over Qs to do an inversion method.
Like an operating Q at that location?
Yeah, to get the operating Q. So the sound pressure here that I'm measuring with the microphone is an operating sound pressure. And then I measure the P over Q during not operation, with that sound source and the same mic to get that P over Q function. And just like the matrix inversion method that we talked about, I can get it. So you can almost think of, when you have the area times the acceleration, that's a bit like the Mount method, if you will. It's not even close, but let's just say it is. And then we have like an FRF inversion method as well when we're doing airborne paths, and that's what this is. So two different ways to kind of tackle measuring the airborne, and two different ways to tackle measuring the structure-borne paths and operating data. But again, the P over Qs, you would use Q source just like you'd have an impact hammer. And then in this case, with the operating Q, it was this operational P times a inverted P over Q that we would measure locally at the location and go from there. Okay. So hopefully that made sense. One nice other thing about Q sources, if you have an accelerometer here, because you're going to measure some structure-borne paths, a P over F that you might measure is the same as A over Q. It's the exact same units. And so you can actually measure your structure-borne FRS with a Q source, which is kind of nice. In fact, that means I can just have a bunch of accelerometers. Instead of going around with an impact hammer and hitting at each location, I can just get all the FRFs at once if I put the Q source here because of those relationships. So instead of impacting multiple locations, just use the Q source ones, which is pretty nice. Okay. Any questions on that so far, Charles?
No, none so far.
Let's talk about this blocked force concept a little bit. And this is just a simple static example. If I had two springs, this is a pretty stiff spring here, and this is a not quite a stiff spring, and I compress it with a force, and I want to use a classic equation to predict forces, like F equals Kx. I would look at the difference here between the delta, and as I compress this, I could use this delta, and if I knew the spring rate here, I could calculate the force. Does that sound right, Stephen?
That sounds, yeah, that should be correct, yeah.
But wouldn't this spring maybe compress a little bit and take up some of that force? You see that purple one got it? So I think one of the challenges we have if you're trying to use, well, a lot of people doing a simulation model, sometimes it's difficult to get the forces accurately. So you might turn to test and ask test people to come up with the forces coming out of a motor, taking into account all sorts of variations. You don't have to build the combustion or all the windings and the electromagnetic forces or whatever it is. That's a pretty complex model. To get those forces, you could try and do simple measurements like displacement across the mount. But the reality is the mount is not the sole stiffness in the system, in a dynamic system, right? It's you're up against something that has some springiness to it. And so when this compresses, our estimate for the force could be a little bit off, right?
Yep.
Especially if the closer these are to each other, the more off it is. That kind of makes sense to you, Charles? I was trying to come up with a simple analogy.
Yeah, it does.
Yeah, good. It's my first time trying this. And I guess the proper solution here is that we would try and take out this spring component if we could, so we could get the true force then for this spring. And that's kind of the concept of a blocked force. But I'm going to explain it more. This is like a static example. I'm going to try and explain it a bit dynamically. So let's start with some more dynamic systems. We all know that if you have masses and springs, you have natural frequencies. I got 3 springs, 4 masses, so I have a very dynamic system with multiple modes. I have, I guess you could call this with an S here, a source system. So in the source system, we got, this is where, this might be a motor, electric motor, or could be a steering motor or something like that. We have a R here, which would be our receiver system. And this V4 could be something like my operator ear. In this case, it's a velocity or a displacement. And there's some sort of forces that are created inside a motor. And those forces operate inside the motor, and that in turn creates a force onto the receiver system. Does that kind of make sense to you?
To me, it does.
Yeah.
Yep.
And what's interesting, in these techniques like transfer path analysis, we try and determine the biggest paths of a system. And we never actually get around to measuring this force input. It's so hard to do. You'd have to have a combustion engine. You'd have to have pressure traces of all the cylinders and be able to translate that to the inertial loads that it creates and forces. It's a lot easier to try and measure the force coming through the mount or the attachment to the receiver and estimate the force coming out of the source. So what's interesting about transfer path is we come up with this force that comes out of the system, out of the source and into our receiver system. And what we kind of want to do is we want to figure out a force here that would make this response the same as this response. So the question kind of is, what is the force here that gives me the equivalent as if this force was being applied? That's kind of tricky because there's really no force, if you will, originating there in the system. The forces originate here and then get transferred out. Yet in transfer path, they kind of act like the forces are starting or created at the receiver entry location. Does that kind of make sense?
Yes.
So I want to create a force that gives me the same output of both systems. So we can take an empirical example like this by having masses and stiffnesses and everything and kind of play around with it. That way we don't have to think about a real thing. There can be multiple attachments, etc. But we got a force input, something like this, and I can get the response output. So all I need to do is calculate a force over here that gives me this same response output. So I could even do that calculation. I can take this system and I can calculate this force And then if I take that force, and I'm going to call that a contact force, because this is kind of the force that we normally see in transfer path analysis, and I apply it to both of these systems. I apply it to the combined system S and R, and I combine it to just R. This will be a pop quiz for you, Charles. In which case would I get the V4 that I expect? In which case will V4 be the same as this V4? Any thoughts on that?
I'll go with the second one there.
This one.
Yeah, that one.
But Charles, there's something missing.
It looks like it's missing, but maybe it's not.
What you're maybe implying is that this force, we don't really need this system present because this force has the effects of this source system in it, so to speak.
Yep.
And so the receiver system only sees this force. So yeah, if we did this empirical calculation, we can see that when we have just system R, that matches the reference. The green and blue curves match. V4 over here, where we have the combined system, does not. So as you said, Charles, this FC is needed for doing this. And in transfer path analysis, that's good enough. We can identify which path is the biggest or most dominant. But part of the problem is that FC ends up being partly dependent on this receiver system. So it's specific for system R. It's not independent of system R. So if we did something where we tried to take this force, and I say, okay, this is the force my motor makes, and I'm going to apply it to my analytical model, I won't get the same results because that FC reflects R and it reflects S. So it has like the influence of those systems in it. Instead, we need this thing called a blocked force or an invariant force. And in theory, this is how we would calculate that. We would connect that source system up to an infinitely rigid, infinitely massive, never vibrate chunk of unobtainium, that is, and calculate the force coming out here. That is a blocked force, and that is not a contact force. Do you think at this point, Stephen, we could say that system R is not influencing our blocked force?
Well, since system R is rigid, it's not influencing that. It's a very defined, rigid structure that is not going to move. So
system R had masses and springs before, right?
Right.
We've removed all that. This is like,
fixed.
Yeah, very, very fixed. So we get a different force, and it even makes sense that we would get a different force in this case due to the same F input. The FB here is not going to be equal to FC, right?
Right.
But this force is kind of interesting to us because we can use this. That's more representative, or it's all representative of system S here. And that's going to be a lot more useful to us in the end for doing transfer path analysis or for using this as a force that characterizes the source and use it in other applications. So let's look at what happens if I calculate this blocked force, this great and wonderful blocked force, and I calculated it at a slightly different location here at the exit of S. So we got FB applied here and FB applied here. Charles, we'll go to you. You answered this right the last time. And I apply it to both of these systems, in which case will, now this is kind of misleading a little bit. V4, well, this V4 is not present in this infinite mass. It can't move. It's equal to 0. So if we still had system R here with its masses and springs, and I was applying this blocked force, in which case would V4 match that original system where we had R?
I'm going to go with the first one.
You're going with the first one, but last time it was this one, Charles.
Yeah, it was. I got a feeling it's not this time, though.
Just going by instinct.
Not only
I think I would set you up. Like, yeah. So you're right. It's this one that matches. You have to, this block force, in order to get the right response of system R here, is has to be applied to both R and S. With R and S present, the two subsystems, you will not get the same result like we did with the contact force if we're just applying it to system R alone. Okay, so that's kind of interesting. Again, the benefit though is I got a new system, system T, with a different mass and stiffness. If I take that block force, it's a little hard to see here, but it's still here, FB, and I apply it to the system ST, I hope to be able to predict this V6. If I take the contact force I had previously calculated and apply it to just T, wasn't that supposed to be correct before, Charles?
It was supposed to be, yes.
But yeah, it is not. This FC, because it was dependent on R, we didn't get rid of the influence of R, we don't get the right prediction for T. Whereas when we apply this block force to the system ST, I actually get the exact same, the response I was expecting. And so to make Stephen's dream come true of like being able to mix and match, like try different system Ts, different analytical models of different vehicle bodies or whatever they are, I'm going to need to apply block forces to it to get the right response if I try and take forces from test. Hopefully that makes some sense for everybody out there.
I think so.
To me, it does. So Pete, what you're saying is that when you replace that input force that you have on the left-hand side here, you take that away because you cannot measure it.
Yeah, that is key.
You measure,
There's no.
Yeah. So you replace that with the blocked force at the connection area, or where source attaches to receiver T, then you would get the same response. That's the key part here. You go from not knowing the input force, you've characterized a blocked force potentially on a infinitely rigid structure, and you're now applying that to the combined system, and you forget about the original input force because you've never had access to that anyway, right?
Yeah, and I think that was key. I probably didn't mention that enough. We took away that force, right?
Yep.
To come up with this equivalent force at the interface between the two systems to get the same response. So
I just wanted to reinforce that, Pete. That's all. That's
Oh no, I appreciate that because I easily look past some of these things. But yeah, and again, this helps us avoid the difficulty of trying to model that source in detail. We can use the operational data coming out of this source to come up with this. All we need is this infinitely large mass or stiffness, right? To attach our structure to.
Actually, if you then just if I may comment on that, if you now look at because you don't necessarily need to attach it anymore to a infinite mass. Would you agree? I mean, if I had the first system with the receiver R and I identified the blocked force a force, which we will call blocked force, to generate the V4 that you had there on that assembled structure, then I have that blocked force. I can replace system R with system T, apply that blocked force again, and still get the right result, right?
Can you repeat that again, Stephen? Well, were you alluding to the fact that there's a few ways to get this blocked force? And one is to put it on something that's infinitely stiff.
Right.
But another way is to do what we term, or other people too, in situ block force estimation, where the system R is available, but there's a way to back out the effects of R using FRFs to these locations to calculate a block force. Is that what you meant?
Well, it's exactly what you, if you look at your slide, Pete, if you now look at the middle situation, your FB in that situation would be like a force you estimate. I mean, this thing you run operationally, it's running, and you estimate a force FB using what we would call matrix inversion typically, yeah, that in that interface area, then you would get the FB as the force that you would need to apply there, right?
Yeah, so I can get a block force from this situation, but I could actually estimate it from this situation as well. What you're
because we just now proved that these two are equivalent.
Well, that's good because a lot of times if you have like a motor or something you're developing, it's probably installed in some sort of fixturing, and that fixturing is not infinitely rigid, right? So maybe I don't have it in my vehicle yet that I intend to put it in, but I might have it in my in a test fixture somewhere where I'm testing and developing that motor. So I can back out the effects of the fixture to get to these block forces, is what you just told me.
Exactly.
Sweet. So all this is something we call component-based transfer path analysis, where we can try and develop these components separately, right? And we envision great things like, hey, maybe you should be able to come up with a component library of proven components that consist of block forces and the FRFs of these subsystems, so you can combine them together so that you can do an ultra realistic virtual assembly of these things and understand what's going on. And I'll pretend I didn't see this misspelling here. So we're
okay.
We're trying to incorporate this technology in our software, and we've been adding components to support Stephen's dream in different versions. So this is your traditional TPA software. I just want to point out a few things. So if I go to add-ins here, there's this component-based TPA. As soon as I turn this on, this little thing that was insensitive here, now I can do block force calculations and other types of calculations to support component TPA. In this summer's release of 2021 test lab, the summer version, there'll actually be an assembler, and this will allow you to take these components, grab them, make simple connections between things, and build up a TPA model of components and easily swap them in and out to assess the effects of different pre-made components in the software. So I guess I at least wanted to point out a little bit about what we're doing software-wise, but I'd also maybe introduce another concept here which is available in the software. So it's called time domain TPA. So if you have the time histories of all this data, so here's like the acceleration time history at a bunch of locations, you can take the time data, and again, the caveat is that all be measured at the same time, so the phasing is correct. And you can kind of push it through the model, so to speak, and it'll generate for you the sound contribution due to each path at the operator ear, so you can actually listen to it. And that's what this is done. And you come in, you can, if you do modifications to the models, you can save those away, and it'll have the modified time histories. And so now I have the model. I hit play. You can see this is moving along in time. And I can right click here and I can say, okay, I want to see the spectrum at this particular location. And it'll show it to me in real time. And I can turn on and off the paths as I'm listening, or turn on and off a group of paths, or even apply filters. So a nice bonus with this TPA technique is if you've acquired everything simultaneously, it's possible to do listening to the results, not just look at a dB versus frequency or RPM and see the change in the level, but to actually hear the difference as well. So, all right. I hope I introduced the basics of TPA for everyone.
Thank you for joining us.
Thanks.
Thank you.